We're on page 97, and on the previous video, topic 18, we did the definition of the nth root of a. We did multiplying, dividing radicals, and we also did adding and subtracting radicals right here. So in this video, we're going to look at rationalizing denominators, and there's two different ways that we can do this. Depending on what kind of problem it is. And we're also going to look at the definition of rational exponents. So let's go first of all and look at rationalizing denominators. So page 97, again topic 18, and what we're going to try and do here is remove the root sign from the denominator. Generally, when we write expressions in algebra, we don't like to leave a root sign on the denominator. So let's say we have x over root a. How are we going to get rid of that? Well, we rewrite this x over root a, and then we multiply the top and bottom by whatever is in whatever this term is here. So we're going to multiply the top and bottom by root a over root a, which is essentially 1. I mean, root a over root a is 1. So when I multiply by 1, I'm not changing anything. So we look at the denominator, we get x root a, and root a times root a is the root of a squared, and the root of a squared is a. So now we no longer have the root sign on the denominator. It's been transferred to the numerator. So as an example, so we have, let's say we have x over root 5. We don't want this root 5 here on the denominator. So we rewrite this part here. We multiply the top and bottom by whatever is here, which is root 5. Root 5 over root 5 is 1, so we're not changing anything. So we get x root 5 on the top. The root of 5 times the root of 5 is the root of 25, which is 5. Note that the root sign is now gone from the denominator. So that's part 1. But part 2 is different because you'll see that on the denominator we have two terms, and they're separated either by a positive or a negative sign. So in the previous, in part 1, we only had one term. Here we've got two terms and they are added together. So what we have to do is use what's called multiply the top and bottom by the conjugate. Here's the conjugate. This is root a plus root b. We write this again, root a and root b, but we put a negative sign here. So if this is plus, this is minus. If this is minus, this will be plus. Note that when I multiply this term times and this term are really 1. I'm multiplying the top and bottom, but in doing so, I'm multiplying by 1 because what's on the numerator here and what's on the denominator here is equivalent to 1. Now, why do I do that? Because I'm going to use the FOIL method. I'm going to multiply the first times the first, which gives me this. And I'm going to multiply the last times the last, which gives me this. And the inner, the inner term is going to be plus b root a. And the outer is going to be minus b root a. So the inner and the outer cancel each other when we multiply by the conjugate. So we only really have the first term times the first term, which gives me that. The last term times the last term, including the sign, of course, which gives me that. And x times this in the brackets, root a minus root b, is this over here. Notice that I've gotten rid of the root sign, which was right over here in the denominator. Yes, it appears in the numerator, but that's okay. So here we're also trying to remove the root sign from the denominator. The denominator involves terms separated by a plus or minus. In this case, we multiply the top and bottom of the expression by the conjugate of the denominator. So when we change this plus to a, when you do the conjugate, it's always the opposite sign of what is here. So let's say I wanted to do, simplify x over root 2 minus root 5. So I rewrite this. This becomes this right over here. So this whole term here is this one over here, and I multiply by the conjugate of this, which is root 2 plus root 5. So the conjugate of root 2 minus root 5 is root 2 plus root 5. And this divided by this is 1. I'm really multiplying by 1 when I do this operation. So I'm not changing anything. Now, as I said, here what happens is we have x times root 2 plus root 5. And here we have root 2 minus root 5, root 2 plus root 5. So first times first gives me 2. Root of 2 times the root of 2 gives me the root of 4, which is 2. The outer term here is plus root 5 times root 2. So that gives me the root of 10 plus root 10. The inner one is minus root 5 times root 2, which is minus root 10. And minus root 5 times plus root 5 gives me minus 5. So you'll notice that this term cancels with this term. So essentially we get the first times the first, as I said, which is 2. And the last times the last, which gives me the minus 5. So 2 minus 5 is minus 3, and the numerator stays the same. Now, it says here the in and outer term cancel each other. That's exactly what I said before. That's the idea of using the conjugate. Now I have the negative sign on the bottom, and usually we don't like on a fraction, we don't like to leave the negative sign on the bottom. I'm going to multiply the top and bottom by minus 1 so that the bottom becomes plus 3 and the top becomes this. I have the negative sign appears on the numerator. So that's the basic way that we handle this kind of problem. As I said, when we've got root A plus root B, we multiply by the conjugate, the top and bottom by the conjugate. The important thing is to do both, numerator and the denominator. So you're not changing anything. This divided by this is 1. So first of all, when you're looking at the problem, if there is no plus or minus sign, you just multiply by whatever is in the root sign here. But if there's a plus or a minus between two terms, as we have over here, then you use the conjugate. Okay, so the last part of the definition of rational expressions is, for example, when I write a to the 1 over n, this is the same as writing the nth root of a. Don't forget, this a is to the power 1, and that's why this is here. The nth root is written here. So, for example, the 1 over 3 would be 3a. The index would be 3, and this would be a to the power 1, or a. So you've got to be able to go from this expression to that expression, or from this expression to this expression. In other words, you've got to be able to go from left to right, or from right to left. So if we have the expression a to the m over n, this is equivalent to saying a to the 1 over n, because this n is this n here, and this m is that 1 over here. We're going to see lots of examples. So when I write this, it's equivalent to writing this. I write this, it's equivalent to writing this. Now, the nth root of a is written as n a, because this is a 1 here, and this is an implied 1 here. This m is this m here. So you've got to be able to realize that this is equivalent to this, is equivalent to that, or vice versa, that this is the same as that, is the same as that. In other words, be able to go, be able to work from left to right, or vice versa. So just to give you a few examples, when we write the square root of x, it implies there's a number 2 here. I've indicated that before because it's the square root. X is x to the 1. So when I write the square root of x, I really mean this. I put this as a power 2 on the denominator here, and this one is this one over here. If I do the same thing over here, this number 2, okay, is indicative of a square root. We have to put the number 2 here, and this is 3. So I could say 3 divided by 2, which gives me that. Another way, I could just leave out the little 2 because it's implied. When I write the square root of x cubed, there's an implied 2 here. The other way I could write it is to realize that x to the 3/2 is the same as x cubed raised to the power 1/2, because if I multiply the numerator here, I get 3 over 2. So I've got to be able to go from this to this, to this, to that, or vice versa. Now, you don't memorize this, you try to understand it, but we'll see applications in problems and as we go into other topics on topic 18. Here again, x to the 2/3. This 2/3 means the cube root. The 2 here means that the x is squared. We can rewrite this. An equivalent expression is just to take the x squared and say it's to the 1/3 power, because 2 times 1 is 2 over 3, which is the same as this. So again, the last example is x to the 4/7, which is the same as writing x to the 1/7 to the power 4. Now, the fact that this is 7 means that we're asking the 7th root. The fact that this is 4 means that this is x to the 4. Because if I simplify this, I can say, if I remove the radical sign, I can say this is equal to x to the 4/7, which is right over here. So you've got to be able to go from this to this to this. So this is a very important page that you should always refer to, and the examples to see its application. And this completes topic 18, page 97.